I'm Suman Matthews, and I will be giving you some formulas in matrices and determinants which would help you in problem solving. So we start with if each element in a row or column is 0, the value of the determinant is 0. The value of a determinant, what happens to it if its rows and columns are interchanged? It remains unchanged. Again, if two rows or columns of a determinant are interchanged, the value of the determinant changes in sign. If any two rows or columns of a determinant are equal, the value of the determinant is 0. Now here, supposing you can see this determinant, every row has k as a factor, so you can take out k and write it as ABC 1, 2, 3, 4, 5, 6. Now the value of the determinant remains unchanged if I do say R1 plus k R3 or C2 minus k C1. So you can add or subtract scalar multiples of any row from any other row or any column from any other column. Now determinant of AB is determinant A into determinant B. A matrix A is symmetric if A transpose equal to A. It is Q symmetric if A transpose equal to minus A. And if A is a skew-symmetric matrix of odd order, determinant of A is 0. Again, if A is a triangle with vertices x1, y1, x2, y2, x3, y3, then area of the triangle will be absolute value of half x1 into y2 minus y3 plus x2 into y3 minus y1 plus x3 into y1 minus y2. And if A equal to Aij, cofactor of Aij will you denote it by capital Aij, and that is minus 1 raised to I plus j, determinant of the matrix obtained by deleting the ith row and the jth column. So adjoint of A is cofactor of A transpose, and minor of Mij is the determinant of the matrix obtained by deleting the ith row and the jth column. So minor is just the matrix obtained by deleting the ith row and the jth column, the determinant of that, and for cofactor you multiply the determinant by minus 1 raised to I plus j. These can be asked as objective questions. Then A into adjoint of A is determinant of A into I3 if A is a 3 by 3 matrix. A inverse is 1 by determinant of A into adjoint of A if determinant A is not equal to 0. If determinant A not equal to 0, you say A is non-singular. If A is a non-singular matrix of order n, determinant of adjoint of A is determinant of A raised to n minus 1. Now, if Ax equal to B, if determinant of A is not equal to 0, the system is consistent and has a unique solution x equal to A inverse B. If determinant of A is 0 and adjoint of A into B is 0, the system is consistent and has infinitely many solutions. And if determinant of A is 0 and adjoint of A into B not equal to 0, the system is inconsistent. Again, if Ax equal to 0, if determinant A not equal to 0, the system has a solution that is x equal to 0. And if determinant of A not equal to 0, but adjoint of A into B equal to 0, the system is consistent and has infinitely many solutions. Now, a matrix is symmetric if A transpose equal to A and skew symmetric if A transpose equal to minus A, and you can write a matrix as a sum of a symmetric and skew symmetric matrix where the symmetric part is A plus A transpose by 2 and the skew symmetric part is A minus A transpose by 2. Again, to find the inverse of a matrix A by elementary row operations, we write A equal to IA and then apply row operations to A to make it the identity matrix and apply the same to I. And to find the inverse of a matrix A by elementary column operations, put A equal to AI. Apply column operations to A to make it the identity matrix on the left and apply the same thing to I on the right. Now, if A is an invertible matrix, A inverse is also invertible, and A inverse transpose will be A transpose inverse. If A is a non-singular matrix of order 3, determinant of adjoint of A is determinant of A squared. If A is a square matrix of order n, determinant of Ka is k raised to n times determinant of A. Adjoint of A transpose is adjoint of A transpose. Also, A into adjoint of A is determinant of A into In is determinant of adjoint of A into A. So adjoint of A will be determinant of A raised to n minus 2 into A. You get it by simply substituting adjoint of A here. So I get adjoint of A into replace A by adjoint of A. Into adjoint of A will be determinant of adjoint of A into In. Now A inverse is 1 by determinant of A adjoint of A. So adjoint of A is A inverse into determinant A. Substitute that here. And here your determinant adjoint of A becomes determinant A raised to n minus 1 because A is a matrix of order n. So you get this as adjoint of A is determinant of A raised to n minus 1 by A raised to minus 1, A raised to n minus 2. This becomes A raised to n minus 2. So hence we have this formula. What is the formula? Adjoint of A is determinant of A raised to n minus 2 into A. And this is an example of a scalar matrix, identity matrix, where each element is multiplied by k, or rather the diagonal elements are multiplied by k. So this is a very useful video because you can have a lot of 1-mark questions based on these formulae. So thank you. Please take a pen and paper and practice these along with me.